Now, I'm going to introduce you to the sample proportion distribution. This is a distribution known as the p-hat distribution, capital P-hat. This distribution is composed of sample proportions. Now, this p-hat distribution is going to follow a normal distribution if the requirements below are met. Now, before we read the requirements, let me help you visualize what we're saying. Imagine you take a sample from the population and you compute a proportion from that sample. You come back with a sample proportion. Now imagine I do the same thing. I go and take a sample from the population, I find the proportion coming from that sample, and I come back with it. If we construct a histogram with all those sample proportions, we're going to see that the histogram follows a normal distribution. That is what we're saying here. And it's going to follow a normal distribution if the three requirements below are met. Okay? So I want you to picture this distribution composed of p-hats. P-hats are proportions coming from different samples. This distribution is the p-hat distribution. The p-hat distribution is going to follow a normal distribution if all possible samples of a given size have equal probability of being chosen. And this is going to happen if we use a simple random sample to select people from the population. If we carry a simple random sample, we're going to have a fixed sample size, which is n, and this is also going to ensure that trials are independent from each other. In other words, we're saying that if we carry a simple random sample, the responses that we get from the individuals in the sample are going to be independent from each other. One answer is not going to influence the other answers that we get from the other individuals in the sample. That is what we're saying. Now, in this class, you can assume that this is true. If you're being asked to construct a confidence interval and you're given some information about a sample that was taken from the population, you can assume that a simple random sample was used. Okay? That will be an assumption that we make for all the problems we consider in this class where we're being asked to construct a confidence interval. The second requirement states that for each trial, there should only be two possible outcomes, success and failure. And that will be the case with all the problems that you encounter in this class, so you can assume that this is true. This is referring to the type of responses, the type of outcomes that you are getting from individuals. Okay? So for example, let's go back to this question here. Here, you only have two outcomes. One of the outcomes is that someone does speak two or more languages. The other outcome is that someone does not speak two or more languages. Okay? So in other words, the outcome is either yes or no. Same thing with the example here below. The outcomes are yes, I do support the new law, and no, I do not support the new law. Okay? Notice for this exercise, you also only had two outcomes. So that is what we're saying with that second requirement. And again, you can always assume that this requirement is met. We're only going to be looking at examples where you have two possible outcomes. Now, the last outcome is that the number of successes, which is n times p hat, and the number of failures, which is n times q hat, these two values need to both be greater than 10. Again, think about it. If you take your sample size times the proportion of success, you're going to get the number of success. If you take the sample size n times the proportion of failures, which is q hat, then you get the number of failures. We are saying that the number of success and the number of failures need to both be greater than 10. For example, if success is defined as someone who does support a new law and failure is defined as someone who doesn't support the new law, we are saying that within your sample, you need to have at least 10 people that said, yes, I do support the new law, and at least 10 people that said, no, I do not support the new law. That is all we're saying. That is what we're saying when we say n times p hat and n times q hat have to be greater than 10. Now, you can assume that this condition is true for the problems that you're going to see in this class. If any of these conditions are not met, then you would say that p hat doesn't follow a normal distribution and you would not be able to construct a confidence interval. So again, that is why I'm saying that when I ask you to construct a confidence interval, you can assume that these three conditions are met, or else you would not be able to construct a confidence interval. Now again, if all requirements are met, we're saying that p hat follows a normal distribution. The center of this distribution is going to be p, which is the population proportion, and the standard deviation of that distribution is going to be the square root of p times q divided by n. And here, let me make an extra note here. Q is always going to be the complement of p, that is 1 minus p. Now, if we wanted to calculate a z-score for a given p hat, right? If you go and grab a sample and you compute the sample proportion and you come back with that p hat, we can go ahead and find a z-score for that p hat. We would find that z-score by taking p hat minus p divided by the square root of p times q divided by n. Notice here we have the observation minus the mean divided by the standard deviation of the distribution. Here below I have a few bullet points that I'm including to ensure that you know what p hat, p, and q represent. P hat is the estimated sample proportion. This proportion is the proportion of success, whereas P is the estimated population proportion. And this proportion is also the proportion of success. Again, P comes from the population. Q also comes from the population, so this is a proportion coming from the population. But here, Q represents the proportion coming from the population, but this is the proportion of failure. So now that you're familiar with the sample proportion distribution, and you know that this distribution follows a normal distribution, assuming all three conditions are met, now you're ready to construct a confidence interval for a proportion. Here below, I have the main 5 steps that we take to construct a confidence interval. First, we're going to read the given information, and we're going to label xn and cl. Our next step is finding a z-score corresponding to the confidence level. This z-score is denoted as alpha divided by 2. So here, let's go ahead and visualize a normal distribution. This distribution is known as the p-hat distribution. The confidence level is going to be the proportion of the area we're trying to capture here in the middle of our curve. The z-score is going to tell us how far we have to go from the center, either to the right or left, to capture the area here at the center. Okay? So your z-score is determined by the confidence level. We denote this z-score using z of alpha divided by 2 because on your calculator, on Google Sheets or Excel, you're going to need to provide the area to the left of the z-score you're trying to find. That area is always going to be alpha divided by 2. Remember, the area on both of the tails is always going to be alpha divided by 2. So the area here on the right tail is also alpha divided by 2. So your second step here is to use a normal distribution to find the z-score. Notice you have the area under the curve and you're trying to find the z-score. Okay? That means we're going to need to use the inverse normal distribution on your calculator, Google Sheets, or Excel. The next step is to calculate the margin of error. And notice for the margin of error, you're going to need the value of the z-score that you found on step 2. You're going to take that value and you're going to multiply by the standard deviation of the distribution. Now, I know that I mentioned that the standard deviation of the distribution is the square root of p times q divided by n. And notice here I have p hat times q hat instead of p times q. The reason why is because we do not have p and we do not have q. P comes from the population. Q also comes from the population. We don't have those values. So the best we can do here is use our sample proportion p hat and q hat. Once you find the margin of error, you're going to construct the confidence interval by taking p hat minus the margin of error, comma, p hat plus the margin of error. The last step is, your last step is always going to be to interpret the confidence interval. And you can go ahead and reuse this sentence here below. We estimate with blame percent confidence that the true population proportion, remember, we're trying to estimate P. So we're saying we are blame percent confident that the true population proportion is between the value that you got for P hat minus E in the value that you got for p hat plus e. Okay? Now, one thing to note is that you should always be using the context of the situation. So you're going to need to explain what the true population proportion represents. Okay? What does that value represent in the context of the situation?